There are numerous types of graph analytics which we will be looking at. These are basically differentiated based on what sort of relationship analysis we are doing. So we can have connectivity analysis, we can have path analysis and traversing, community analysis, centrality analysis, and pattern matching. Now let's look at each one of these in detail. The first one is the connectivity analysis. This is basically getting an idea of the graph structure. Okay, how big the graph is, what are the number of vertices, what are the number of edges, and what is the degree distribution. Okay, and the degree distribution refers both to the in degree of a vertex. So you know the number of edges pointing to a vertex, out degree, number of edges pointing out of the vertex, and the complete degree would comprise of both of these. So it is the number of all of the neighbors of a vertex in a unidirectional graph. With respect to vertices and edges, there are two things that you need to see. Volume. The number of edges increase quadratically with respect to the number of nodes. So you need to see how many connections there exist between the nodes. And then the other is the velocity. How frequently a new edge or vertex is added to the graph. Then we look for highly connected nodes. These are the nodes that have high in and out degree. For any social analysis, these are the influencers. These are the people that have the most outreach to other ones. Or these are those congestion points if I consider a geographical system or traffic map. So these are of importance to us. Then we check for graph robustness, how easy it is to break the graph by removing a few nodes. So in this scenario, if you see that if I simply remove the B node, I'll have two disjoint graphs over here. Okay? So that's another important thing that we need to consider both for social analysis, for the graphical analysis, biological analysis, and all of those. This is something that is of value or importance to us. We check for connectivity coefficient. This works as the cost. So we need to see what is the minimum number of nodes that we need in order to break a graph into multiple graphs, two graphs, let's say. Then we see the connectivity. If X is reachable from Y or Y is reachable from X, what are the different options we have there? Strong connectivity is when these are bidirectional, X can reach Y and Y can reach X as well. We can also do graph comparisons where we see if the number of nodes are same, if the number of edges are same, if the ratio of nodes to edges is same, or if that is different, then in and out degree histogram can be created to check the comparison or see the similarities between two graphs. We can check the connectivity coefficient as well in order to see the similarity between numerous graphs. Next, we can see if the graph is fully connected or not. In terms of fully connected, we say that each node has edges to all of the other nodes or edges. Okay? So given your position at any one node, you can literally access all of the other nodes inside your graph. And then we check for terminal nodes, which are the nodes that have only incoming edges but no outgoing edges. So if you somehow get to this one, you're to a dead end and there is no path forward. There are some unreachable nodes. Okay? The unreachable nodes are that have no incoming edges. Okay? So you can start from over here, but you cannot loop back to this place. So you cannot go to that. You can at some places only start from that. Those are unreachable nodes. Then there are hubs and there are authorities. Hubs are the one that have the most number of high in degree, the most number of incoming edges. Okay. In social networks, these are talkers. These are listeners. These are the ones that have the most amount of information influx. Okay. And then there are authorities that have high out degree. These are the influencers. These are the talkers. These are the ones that have the maximum outreach. Okay, so these are important in understanding the dynamics of any network. The second is the path analysis and graph traversing. Okay. Now, path analysis, in simply defining a path, we say that this is a set of ordered edges between any two given nodes, node X and node Y. Okay. So I start or I choose one node as the starting node, and then I see what path I can traverse to get to my destination node. So in this case, I can go from C to B, B to E, and E to again maybe B or D, and from this I can get to the A1. Okay, so a path simply defines the set of edges between any two given nodes. A cycle is when this path has redundancy, or you can say that the start and the edge is the same, and you access the in-between nodes to get to the same point. So you get the source or destination are the same. Then a trail is a path with no repeated edges. You travel through all of the edges only once. I can redo the nodes. Okay, the nodes are being done maybe twice, but not the edges. So only one edge or one path was traveled. Okay, a tour is a cycle traversing all nodes only once. Okay, so you can go through all of the nodes, all of the different vertices, but you can travel them only once. Okay. Then reachability is simply if there does or does not exist a connection from D to C or one node to the other node. Shortest path, this is something you must be familiar with. Shortest path is the minimum distance between any two given nodes. This can be breadth first search, and in many applications we use Dijkstra algorithm for this. Then there is the best path. In weighted graph, we can have a path that optimizes our cost function or optimizes our goal. This satisfies all of the possible constraints that might be there. A graph diameter is the longest, shortest path between two reachable nodes. Okay. So it is the shortest path with containing the most amount of edges between them, shortest cost path with the most amount of edges between them. And minimum spanning tree is where all the nodes are connected, but with no cycles. So we again find the minimum weight pathway, but we do not, it is acyclic or there are no repetitions or recurrences in there.